Today we're going to look at factors affecting equilibriums. I think in class today we looked at calculating equilibrium constants. That kind of went along with what we did in our ChemQuest a couple of days ago, as well as just that whole ice table concept, which we kind of looked at first semester with limiting reactants. Alright, so today, if you're kind of following in your notes, we're going to do Roman numeral 3. And we're just going to call it factors affecting equilibrium concentrations. So I'm just going to put that in brackets. Alright, so this mainly comes down to a Frenchman's name, and his name was leChatelier's. It's leChatelier's. leChatelier's principle. That should be here, I-N-C-I principle. Alright? And leChatelier's principle basically says if stress, and we're going to kind of look at different stresses here in a second, but if stress is applied to a system, at equilibrium, equilibrium will shift to reduce the stress. And this is a super important concept. Comes up on the AP test quite often, whether it's in the multiple choice or even in the free response questions. Just this idea or concept, which we kind of have given the name leChatelier's principle. All right, it will never be enough just to give an answer as leChatelier's principle, but you'll have to explain how leChatelier's principle applies to the situation that you're asked about. All right, so there's several situations that it can apply to, and our first one is going to be a change in reactant concentration, so I just have it in brackets, or product concentration. Brackets. Okay? So if we have this theoretical equation, or if this theoretical I guess equation that works, of hydrogen plus iodine yields hydrogen iodide, alright, and it's an equilibrium equation because we have kind of our arrows going both directions. Typically, our K for this is going to look like this, where Kc is going to be Hi concentration squared over hydrogen concentration times iodine concentration. Okay, and that is what our Kc looks like, right? Just goes right along with anything we've done with concentrations. We can also say that this is equal to Q at equilibrium. Alright? But again, Q is just our reaction quotient. It's just what our concentrations happen to be at any given time. Might be what we start with. It might be what it be before it establishes equilibrium. But Q is at some point in time. Okay? And if Q happens to be at equilibrium, then Q equals K. Alright, so a couple things can happen. The first thing we can do is we can add more reactant. Right, so kind of if we go back to just this idea of adding reactants or products or changing reactants or products. So if we add reactant, okay, that would mean in this situation that we're going to have a positive change in either H plus or I2. Okay, so we're changing it positively. We're making it larger. So that means that our Q, or our change in Q, is going to go down. Alright? So it is going to be less than, okay, so it's going down. So we might say Q is less than K. So how will equilibrium reestablish itself in order to make Q back to the size of K? Well, in order to do that, if we're adding a reactant, more product is going to need to be made. Alright? So we might say forward reaction forward reaction occurs to reduce stress. Okay? The second thing we can do is we can add product. Alright, so in this case we would be positively changing HI concentration. And if we positively change HI concentration, it means Q is going to get larger, alright, or Q is going to be greater than K. So how can we get Q to be a smaller number? Well, we're going to need to increase our denominator values, and our denominators are our reactants. So we might say that the reverse reaction is favored. Okay? A couple other things can happen is we might remove reactant. So instead of adding reactant, we might be able to remove part of our reactant. So if this happens, we are negatively affecting our change in H2 or I2. And what that essentially means is that if we're taking away, if we're making these smaller, our overall quotient or our division is going to get larger. So Q is going to increase with a smaller denominator. And again, our reverse reaction is favored. So if we take away reactants, the equilibrium is going to shift so that we make more of those reactants to get K back. And then finally, we can remove product. And if we remove product, we essentially have a negative change in HI. So we are reducing our numerator. And if we're reducing our numerator, our Q is getting smaller. So our Q is less than what K is. So how is it going to establish equilibrium again? Well, the forward reaction will be favored so that we can make some more product. Alright? So that is what happens if we change concentrations. There's a couple other things we can change as well. So we're going to go back to C and say if we change pressure or volume. I'm just going to store those as P's or V's. So we change pressure or volumes. If we're talking about pressures and volumes, we're really referring to gases. So change pressure or volume of gases. And we're just going to put the caveat in at constant temperature. So everything else is constant other than pressure or possibly volume. So again, we're going to come up with an equation. We're going to say 2 moles of hydrogen. We're going to say those are in the gas phase, plus 1 mole of oxygen in the gas phase is going to create 2 moles of water. And we're going to call that in the gas phase as well. And that all works. Right? And this is a reversible reaction. So we can either be making water or at a certain pressure and volume that can be established and we have equilibrium going back and forth. So in this case, instead of having a Kc, we're going to have a Kp, alright, because it's pressures, and this is going to equal water in the numerator, and again, I'm using parentheses, not brackets because it's not concentration, squared, all divided by the partial pressure of hydrogen squared times the pressure of oxygen. Okay? And again, at equilibrium, we could say Q equals this, again, at equilibrium. Alright, so a couple things we can do. And kind of a couple things, notice this. On our reactant side, we have 3 moles of gas. And on our product side, we have 2 moles of gas, which is important. So a couple things here. The more moles we have, the higher the pressure is going to be. Pressure is related to how often molecules hit the sides of whatever container they're in. So if we have more moles of gas, they're going to hit the sides of the container more often, which means our pressure goes up. Okay? So, a couple situations can happen. We can either increase or change our pressure positively. So how can we do that? We could start compressing whatever container it's in. Okay? As we compress that, those molecules hit the sides more often because there's less distance to travel between the sides, so we can increase the pressure. So if we increase the pressure, our reaction is going to want to shift to the side that has fewer moles of gas. Alright? So if we increase the pressure, in this case, it's going to shift towards fewer moles. because that essentially reduces the pressure. Shift toward fewer moles of gas. So in this particular equation, we might say that the forward reaction is favored. Although it's possible to have a reaction where we have more moles of gas on the product side than we have on the reactant side. And then the second thing we can do is we can make our container larger, so we'd actually be decreasing the pressure. Right? And if we're decreasing the pressure, we are going to need to reestablish a higher pressure. Alright? So if we're reducing the pressure, we're essentially making our denominator, or in this case, well, it really has nothing to do with denominator, numerator, my bad. If we're reducing the pressure, it's going to want to shift to where we have more moles of gas so that the pressure can be artificially increased. So we might just say shift to more moles of gas. And in this particular equation, we would say that the reverse reaction would be favored. Alright? Because that would reduce our stress. Alright. Another thing we can do, which is going to be letter D, is a change in temperature. And a couple things on this one. The first thing we're talking about is endothermic reactions. Right, endo, we might have something kind of like this. We're going to have reactants, and they're going to go towards products. And essentially, if it is an endothermic reaction, we are needing to supply energy for the change to take place. So really, we're going to put heat, and it's going to function as a reactant. Okay? So heat plus reactants is going to yield products in an endothermic reaction. So a couple things we can do. If we increase the temperature, or we can decrease the temperature, but if we increase the temperature, we're essentially adding more heat. Alright? So if we're adding more heat, how is this going to shift so that we can get some of that heat taken away? What's going to happen is, if we add heat, it's going to make more product, okay? So it's going to use up this reactant because we're actually adding more reactant kind of as our heat. Even though that does not show up in our K expression, this is just going to be products over reactants, and heat does not show up here, it kind of acts as an artificial reactant. Okay? So if it's an endothermic reaction and we change the temperature positively, our reaction is going to shift to more product and less reactant. More product or less reactant. Alright? If, though, we reduce the temperature, okay, and this is an endothermic reaction, if we reduce the temperature, it's going to want to make more heat. Right? So in this case, it's going to shift backwards, and we're going to make more reactants, because as we make reactants, what else do we produce? We produce heat. Alright? There should be a double arrow. Or we can make more reactants, or less product. Come on, eraser, there we go. More reactant or less product. Alright, the reverse of this is also going to be true. So we can talk about endothermic reactions, or we can talk about exothermic reactions. And in an exothermic reaction, again we have reactants that yield products. But in an exothermic reaction, heat is essentially a product, alright? Because we are producing extra heat, which is given off to the surroundings. So in this case, again, we could raise the temperature on an exothermic reaction, or we could lower the temperature on an exothermic reaction. If we raise the temperature on an exothermic reaction, it's essentially like we're adding more product. So how's that going to shift? If we're adding more product, it's going to want to make more reactant. Okay, it's going to want to use up that heat. So more reactant is produced, and less product. If we take away the temperature, okay, if we lower the temperature, it is going to want to make more heat. So we would say more product and less reactant. And again, that is just to, again, reduce the stress that we're applying. And then the last thing, and this will wrap it up, is simply catalysts. Right? So again, catalysts change the speed of reactants by lowering the activation energy. So essentially catalysts have no effect. Again, this is a question they like to ask in the AP test. So catalysts have no effect on K, or on equilibrium. What do? They simply speed up reactions. Okay? Speed up reactions by lowering activation energy. E sub A. Alright? So it gets to equilibrium faster, but it still is going to have the same equilibrium constant. Alright, so that is it. leChatelier's principle is super important, and that is all I have for you tonight.